A box plot flagged a 199 kilobyte file on this host. I never told it to look in temp. I never told it 100 kilobytes was suspicious. It looked at this host's own data and figured out on its own what didn't belong. Welcome back to Threat Hunting 201. I'm going to show you the one technique in this series that doesn't need you to already have a theory. Every technique so far, stacking, grouping, clustering, anomaly detection, needed you to bring something, a field to rank, a list of suspicious artifacts, a distance metric, a baseline. This one just needs the data. This is technique 6. Exploratory data analysis and visualization. Quick recap. Stacking ranks, most common, least common, one field at a time. Grouping links, you already suspect a set of artifacts, and grouping shows you which ones show up together. Clustering finds structure across multiple dimensions at once without you telling it what similar means. Anomaly detection tracks one host's own metric drifting away from its own history over time. All 4 of those need you to bring a starting theory. Today's technique is different. Exploratory data analysis in Splunk's own Threat Hunters Cookbook is described as understanding what comprises your data before you have decided what you're hunting for. In practice, that means 3 things: summarizing the shape of a distribution, quartiles, median, spread, visualizing the relationship between 2 variables to see which points break the pattern, and doing both of those on a data source you might be looking at for the first time. Notice what's not in that list: no time window, no pre-built model, no list of known bad artifacts, just what does this specific host's data actually look like right now. Here's the real difference. And it's not just academic. Every technique before this one makes you decide the threshold before you look at the data. Stacking, you pick top n or bottom n by hand. Grouping, someone already told you which artifacts are suspicious. Clustering, you pick the dimensions and trust the algorithm's distance math. Anomaly detection, you build weeks of baseline first, then set a deviation threshold. EDA flips that. You don't set the threshold, the data sets it. A box plot's outlier boundary Q3 plus 1.5 times the interquartile range is computed fresh from whatever's actually sitting in this environment right now. That's not a minor technical detail. It means this technique still works on day one, on a host you've never profiled, on a data source you opened for the first time this morning. Every other technique in this series needs history or intel first. This one doesn't. Let me put this in a table, because this is the one thing I want you to remember. Stacking ranks a single field and you set the cutoff. Clustering groups across multiple dimensions, and the algorithm sets the boundary based on distance. EDA and visualization profiles a distribution's actual shape, and the data itself sets the boundary. No algorithm tuning, no distance metric, just quartiles. That last row is the whole episode. Everything we do today, the threshold comes from the data, not from us. Here's a real gap. Clustering from episode 4 needs you to already believe certain dimensions, matter, parent-child pairs, structural string features, whatever you picked. If the thing that's wrong doesn't live in a dimension you selected, clustering never sees it. Anomaly detection from episode 5 needs weeks of baseline history for a host before it can say what's normal for that host. If you just stood up a new endpoint today, or you're looking at a data source your organization has never analyzed before, there is no baseline yet. Anomaly detection has nothing to compare against. EDA doesn't have either problem. It doesn't need you to pick the right dimension in advance, and it doesn't need history. It needs one snapshot of data and a bit of arithmetic. Use this when you're scoping a data source you've never hunted in before. You don't know what's normal yet, so you can't set a threshold by hand even if you wanted to. Use it when you suspect an outlier exists but you genuinely don't know where the line is, and use it as your very first pass on brand new telemetry before you've built a single anomaly detection baseline or picked a single clustering dimension. This is where every hunt should start when you are new to the data. In Splunk, this whole technique leans on one macro box plot bundled with the machine learning toolkit. You pipe your numeric field in and it hands you back the 5-number summary min Q1, median Q3, max, plus a chart. ESEQL doesn't have a box plot macro, but it doesn't need one because the actual math behind a box plot is just percentiles. Stats Q1 equals percentile field, 25, 3 equals percentile field, 75 gets you the same 5-number summary, and from there the outlier boundary is one line of arithmetic Q3 plus 1.5 times Q3 minus Q1. No macro, no toolkit dependency, just the same statistics written out. Let's build all three of these live. First, a file size box plot that has to work around 1,000 legitimate Windows Update files to find one real 199 kilobyte drop. Second, a DNS query scatter that catches a process resolving domains it's never asked for before. Third, I'm going to try to break my own second hunt, find a legitimate process that looks just as suspicious on the same chart, and show you why the ratio alone isn't enough. All three ran against a real Caldera-simulated raccoon stealer infection I triggered on this lab today. Nothing here is synthetic or pre-staged. Let's go. Hunt 1. In Splunk, you'd start this with field summary or box plot against your file index to get the 5-number summary. Here's the ESQL version from logs endpoint to events.file default, where file.size greater than 0, stats Q1 equals percentile file size 25, median equals percentile file size 50, Q3 equals percentile file.size 75. Straightforward. One filter to skip 0-byte events, one stats pulling 3 percentiles. Could stacking find this? No, stacking would need you to already pick file size as the field to rank and guess a cutoff. Could clustering? Also no, clustering needs multiple dimensions. This is one field's own spread. This only works because we're asking the data what its own normal looks like, not asking it to match a rule we already wrote. Let's run it and see what our real endpoint's file size distribution actually looks like. Q1 sits at 1659 bytes, median 6595, Q3 46,834. That's already telling you something. Half of all files this host touches are under 6.6 kilobytes and 3/4 are under 47 kilobytes. Most files on a Windows box are small. Config fragments, cache entries, tiny logs. Now the outlier math. Interquartile range Q3 minus Q1 is 45 as 175. Standard box plot rule, anything past Q3 plus 1.5 times that IQR counts as a statistical outlier. That comes out to 114 and 596 bytes. Not a number I picked, not a round number at all. That's this host's own data telling me where unusually large starts today right now. Let's filter for it. Where file.size greater than 11496, and that's over 1,000 rows. Not what I wanted to see, but this is real and I'm not going to pretend it isn't. Let's look at what's actually in here. Sorting by size, the top of the list is legitimate. An 827 megabyte Windows update package, several 700 megabyte WinRE recovery images, Edge installer temp files in the hundreds of megabytes. This host went through a real Windows servicing cycle recently, and Diasm and SVKiost both write enormous legitimate files during that process. So the box plot's threshold is correct. These genuinely are statistical outliers, but 1,000-row list isn't a hunt result, it's a haystack. Here's what an analyst actually does next. Stop looking at individual files and look at how often each process shows up on this outlier list. Stats n equals count star by process name on the same filtered set. Excluding the processes I can already see are bulk system services, Tism host, SVKiost, wow Core, trusted installer, setup.exe, OneDrive setup, Mo Core worker, what's left, MSec Core S, vlib with 129 hits, system with 118, MS Edge Web View 2 with 45, all still legitimate, still recognizable installer or update processes, just less obviously so at first glance. And then right at the bottom, one process, one file, PowerShell.exe, not 129 times, not 45 times, once. Every other process on this list, even the ones that aren't obviously Windows Update, shows up dozens of times because it's doing bulk repeated legitimate work. A single unexplained large file from an interpreter is structurally different from all of them, not because of its size alone, but because it's alone. Let's look at that one row directly, where process.name equals PowerShell.exe and file dot size greater than length forward 596 cookies.txt 199,094 bytes path c colon backslash windows backslash temp backslash raccoon underscore staging written by PowerShell into a folder named after exactly what it is. Could a fixed rule like alert on any file over 100 kilobytes in temp have caught this? Maybe. If someone happened to guess that exact number for this exact host, but that number isn't universal, it's specific to this host's own file size distribution today. A box plot doesn't need you to guess it, it computes the right number for whatever environment you're actually in. Hunt 2 moves to DNS. Quick flag before we start. Yes, episode 4 also had a DNS hunt. That one looked at domain name structure, how random or algorithmic domains characters look. This one ignores the domain names completely. It only looks at behavior. How many times does a process query DNS? And how many unique domains does it actually ask for? In Splunk, you'd build this with stats count DC of domain by process and then drop it into a scatter plot panel. ES-SQL version from logs endpoint.events.network default, where dns.question.name is not null, stats query underscore count equals count star, distinct underscore domains equals count underscore distinct dns.question.name by process.name. Could grouping find this? No. Grouping needs a predefined list of suspicious domains or processes. We don't have one going in. Could anomaly detection? Also no. At least not day one. It needs a time baseline for this specific host's DNS behavior first, and we don't have weeks of history. This works right now on the very first day because it's just a ratio between two counts. Let's read the shape of this. Task host w.exe 1338 queries only 3 distinct domains. That's a 446 to 1 ratio. It's asking the same handful of endpoints over and over, which is exactly what a background sync or telemetry process does. switchost.exe 932 queries 54 domains 17 to 1. Still repeat heavy, still normal for a Windows service juggling multiple update and licensing endpoints. OneDrive.exe 553 to 46 12 to 1. Every real process on this host sits somewhere between roughly 12 to 1 and 446 to 1. Normal software talks to a small, stable set of endpoints over and over. That's the pattern this scatter plot is actually testing. Now look at PowerShell.x. 24 queries, 19 distinct domains, that's 1.26 to 1. Almost every single query goes to a domain it's never asked for before. Nothing else on this host is anywhere close to that ratio. Let's pull the actual domain list where process.name equals PowerShell.exe and the DNS.question.name is not null. 6SM AYA 9E3MR052 VUR4077B 6WC 6FE.telemetrysync.org. Another one OLY1E2 1X RHPK32ST ABZ.malware-c2.io and another C14 VZA8144 FFGD OHAQ20GJZS1D 3TNECJ.update -svc.net long random looking labels, different parent domain each time, all next domain, which is expected. A real DGA doesn't need most of its generated domains to resolve, it just needs one eventually, and the attacker only has to register that one in advance. That's the scatter plot catch. One process sitting off the trend line every other process on this host defines using nothing but a query count to domain count ratio. Hunt 3, and I want to be honest about why I built this one. My first version of this segment reused Hunt 2's exact same data to make the exact same catch again through a different chart. That's not a third hunt, that's padding. So I scrapped it and asked a harder question instead. Does the ratio from Hunt 6.2 on its own actually hold up, or can it be fooled by something completely legitimate? Go back to Hunt 2's own results. Moso core worker.exe 138 queries, one distinct domain. That's a 138 to 1 ratio. High repetition, low diversity. Structurally, then that's the opposite shape from a DGA beacon, but opposite shape isn't the same as obviously safe, and I want to actually check that assumption instead of asserting it. Let's pull its raw query timeline, where process.name equals mo-uso core worker exe sort at timestamp asc. Every single query is to settings win.data.microsoft. com. That's expected from the diversity number already. But look at the timestamps. 22.16, then 0001, then 03 in 01, 03 in 01, 03 in 01, then 1601 three times, then 1601 four times. These aren't randomly bursty like human browsing, and they're not on a tight fixed second interval like a beacon either. They're landing within a minute or two of specific clock hours. That's a scheduled Windows update check-in, not a person clicking around, and not the exact cadence a malware beacon usually runs on. Here's the actual problem this creates. If I'd built Hunt 6.2 around the diversity ratio alone, no domain content, no second signal, a legitimate scheduled polar with a tight low diversity semi-regular pattern could plausibly land close enough to a real beacon shape to warrant a second look. That's not a flaw in the technique, that's a real limit of using one lens by itself. So what actually tells these two apart? Not the ratio, process reputation and code signing. Moyuso core worker.exe runs from c:\windows\system32 signed by Microsoft. PowerShell.exe running our beacon is a legitimate signed binary too, but it's being used to do something its normal call pattern never does, from a script context not launched by Windows Update's own scheduler. That's the real answer, and it's not a clean one. EDA gets you to these two look similar on this axis, but closing the gap needs a second independent signal layered on top. That's genuinely where this series is headed next. Combination methods using more than one lens together on purpose. Today was about learning to build each lens correctly first. Let's talk about why this matters beyond just these three queries. A black box anomaly score tells you a number is high. It doesn't tell you why, and it definitely doesn't tell you what high means for this specific environment on this specific day. Every number in this episode is one you can defend line by line out loud to another analyst. Q1, median. Q3, three sorted values. IQR, one subtraction. The outlier boundary, one multiplication and one addition. The DNS ratio, one division. None of it is a trained model you have to trust. All of it is arithmetic you can re-derive by hand if someone asks you to justify an escalation. And Hunt 6.1 proved something else worth remembering. The threshold itself isn't fixed. Run this exact same query on a different host, a different day, after a different patch cycle, and Q3 plus 1.5 IQR will come out to a different number, because it's computed from whatever's actually normal for that environment, not from a number someone picked once and never revisited. 3 real hunts today, all against a live Caldera-simulated infection I triggered specifically for this episode. Nothing pre-staged, nothing synthetic. A box plot found a 199 kilobyte staged archive by deriving its own threshold from this host's own file size distribution, then needed a second pass ranking outlier processes by frequency to cut through 1,000 legitimate Windows update files. A scatter plot caught a DNS beacon by its query to domain ratio alone, no domain name analysis required. And stress testing that second hunt against a real legitimate process, Windows Update's own scheduled polar showed exactly where a single EDA lens stops being enough on its own. Next episode, we're doing combination methods, the last technique in this series, layering multiple lenses together on purpose, the way Hunt 6.3 just showed you is sometimes necessary. The Caldera ability behind today's attack and the real telemetry it generated is open source. Link in the description. Replay my exact dataset or run the simulation yourself. If this helped, tell me on LinkedIn. I read every comment. Stay curious. Keep hunting.